All right, we are ready. Oh, last day was a doozy, right? We did polynomial long division, so we're gonna keep doing, we'll do 2 more examples of that, just so we get the hang of it. And then, but I encourage you to work through all those problems, because the more you do, the quicker you'll get, and it'll just be kind of fun. So, but just as a reminder, right, test number 2 is on Tuesday, November 17th. On Tuesday, November 17th, during class time, of course. During class time. Okay. And we'll do the same format that we did last time, where you get your questions on WebAssign, you work through those problems, and then you send me your work by email when you're done. Okay. Just so I can make sure that when you go through it. Okay. But we'll talk more about, or just so I can make sure that you've submitted all your answers later when I go through your tests. But we'll talk more about that closer to the test next week. Okay, so for review, we talked about polynomial long division. Log division, that's different. Long division, where, okay, so we established how do we do this long division, and then we also talked about the factor and the remainder theorem, or more importantly, the remainder theorem. The remainder theorem says, that if you have some polynomial p of x divided by x minus c, okay, then the remainder that you find r of x is going to be p evaluated at c, right? So the remainder of this division is the original polynomial evaluated at c, and that's kind of weird, but it can be kind of useful, right, to know. So so if you ever have to evaluate the polynomial at c, then if you have the remainder, you already know what it is, right? So that's kind of a cool tool. The factor theorem. The factor theorem says that if the remainder is 0, right? So if we have p of x over x minus c, and the remainder is 0, then of course x minus c is a factor of p of x. So if p of x over x minus c gives r of x equal to 0, right? So no remainder, then x minus c is a factor of p of x, right? It means you were able to divide out x minus c cleanly, right? Because the remainder is 0. Oh, this doesn't look like x. Okay. So let's do 2 more examples here. I'll pull in, where are we here? I told you to do as many of these as you could. And the ones that I've picked, unless you have ones that you want to go through instead, the ones that I've picked to go through are, which one was it? 11 I wanted to do, and 14. Okay. We also talked about last day that we can represent the answer in 2 different ways. They're equivalent, right? So they're the same. It's just a matter of, have we multiplied both sides by d of x here to make this, right? And so maybe I should put that in before we finish our review. The result of p of x divided by d of x can be written in two different ways, or in two equivalent ways, can be written in two equivalent ways. Oops, that didn't look good. Equivalent ways. The first one is that p of x over d of x is equal to q of x plus the remainder of x over d of x. If you think about something that we know, right, 5 over 2, for example, we know is 2.5. Well, the quotient there is 2, and then 1 over 2, right, is the remainder, 1/2. So here, right, think 5 over 2 is 2 plus 1 over 2, right? A remainder of 1 over the divisor 2. Okay. So now, what we can do is we can multiply this d of x over here. So what we can do is we can have p of x over d of x, and then multiply by d of x is equal to q of x plus r of x over d of x. But what I do to one side, I have to do to the other side, right? D of x. And so this is going to cancel. Bing, bing, that was the whole point. And then, so we get p of x is q of x d of x plus r of x over d of x times d of x. But of course, these are going to cancel out. So you're just left with p of x is equal to q of x d of x plus r of x. Right, so these two are equivalent. Sometimes I'll just ask you, what's the quotient, what's the remainder? Or sometimes I might get you to put it in this form, right? Or I might get you to put it in this form. As long as you're able to figure out what the quotient is and what the remainder is, arranging your answer is not the hard part, right? Finding the quotient and the remainder, that's the hard part. Okay, so that's where we'll end our review. I just wanted to point that out, that they're equivalent. Okay, so these two blocks, they're just getting you to answer in two different ways, but we should be able to do all of these. There's no difference between them. And we're going to use the long division. The synthetic division is in your notes, but I'm not going to cover it because I don't want to cloud your brain. Okay, so I just want you to know the long division, and if you prefer the synthetic, that's fine. Okay, so I'm just going to find q of x and r of x, and then you should be able to arrange your answer in either way. So let's do 11, unless there was one that you wanted me to go through instead. But 11 is one of the hardish ones. So let's do that. And then 14 is one of the trickiest ones. So that's why I picked that one. So 11 says p of x is 2x to the 3 minus 3x squared minus 2x divided by d of x, which in this case is 2x minus 3. Okay. So first thing I'm going to do is I need to make sure that I've got all, starting from my degree, right? So the highest power of x, I need to have all powers of x after that, right? And so what you'll see here, or what we'll see later, is we need to have, so we have x to the 5, that's our highest degree, our highest power, and then to the 4, there's no x to the 3, so we have to squeeze one in. There's no x squared, but there's no x, so we have to squeeze one in there, and then we can go to our constant. So we have to kind of blow this up a little bit in order to have spaces for each of these x's. Okay, so we'll keep that in mind for 14, right? But as you go through here, 4x to the 3 going to x means you need to insert a little x squared here before you can keep going. In this case, we're all decreasing. Here, x to the 4, x to the 3, there's no x to the 2, but there's an x, so you need to insert an x squared. What you do is you just take 0 times x squared here. Sorry, that was a long sneeze. So here, need to make sure we have all powers of x starting from the highest power, in the numerator. So we don't care about the divisor, right? Dividend divisor. We only care about that for the numerator. Okay, so what this looks like is I have 2x minus 3 dividing into 2x to the 3 minus 3x squared minus 2x. Okay, whatever I find up here is the quotient q of x, and then eventually I end up with the remainder r of x, if there is a remainder. What we said, the factor theorem says that if there is no remainder, if the remainder is 0, then 2x minus 3 is a factor of this thing, right? Because I was able to pull it out clean. I won't be able to, but that's what it would mean. So what do? We take this leading term and divide it by the leading term in the divisor. Okay? So the work I need to see is the work here in your actual long division. What I always end up having is just kind of scrap notes all the way along here. So what I might do is I might scoot this over a little bit here and just kind of keep a little, I'll try to keep my scrap work over here, okay? Because we went through and we established all the steps for doing these last day. So now I'm going to do it a little bit quicker. So I have 2x to the 3 divided by 2x. So I'm going to do that here. 2x to the 3 divided by 2x is x squared. Okay. The 2 and the 2 cancel. X to the 3 minus 1 is x squared. So I have x squared up here. Now what I need to do is I need to do x squared times 2x minus 3 to figure out what value goes down here. So now I do x squared times 2x minus 3 is 2x to the 3 minus 3x squared. Okay. That value goes here and gets subtracted. So 2x to the 3 minus 3x squared, and then I subtract it. The whole goal here is to have this fall out and have it be 0, right? And so that's what we're forcing. We're forcing this to be 2x to the 3, right? By saying, okay, I'm going to take this times this and then subtract it. So this becomes 0. Negative 3x squared minus negative 3x squared is actually negative 3x squared plus 3x squared. So that's unexpected, but it's plus 0x squared. So plus 0, technically x squared if you want. You don't need to. You can just have 0 if you want. And then we need to bring down this negative 2. What's actually going on is negative 2 minus 0. but I find that that gets a little bit messy, so I just bring it down minus 2x. Either way, it works out to be the same. So now I do the exact same thing that I just did, but I just use 0 divided by 2x. So 0x squared divided by 2x, well, that's going to be 0. So 0x squared divided by 2x is 0. So I get plus 0. And then a little bit tricky, right? 0 times 2x minus 3. But that's why I like this question, right? Because it introduces zeros and it's kind of like, oh, what do I do? But now 0 times 2x minus 3 is, of course, 0. So what you get is you get 0 times 2x minus 3. Oops, I don't know why I'm writing on an angle like that. 0 times 2x minus 3 is 0x minus 0. Oh yeah, I guess it's 0x. It doesn't actually matter because it's 0, but just for kind of keeping things gravy, it's 0x. Because it goes to 0, like I said, it doesn't matter, but just so we can always apply the same procedure, how about we keep it at 0x? That's fine. If you just wrote 0, that's fine too. Let me change this. 0x times 2x minus 3 is 0x squared minus 0x. Okay. So this becomes 0x squared minus 0x. Once we subtract that, though, we get 0 minus 0 is 0. Negative 2x plus 0x is, of course, negative 2x. Okay. You could have skipped this section, but I don't recommend it because then you might forget something, right? So I would probably just stick with it and not jump through the 0x squared right to the negative 2x. Depends on how comfortable you are, though, because what you'll see is this is just 0, and then when it picks back up again is at negative 2x divided by 2x. So now we get negative 2x divided by 2x is negative 1. So minus 1 up here. Minus 1 times 2x minus 3. Minus 1 times 2x minus 3 is negative 2x plus 3. So down here, negative 2x plus 3, which I'm subtracting here. Negative 2x plus 2x is 0, and 0 minus 3 is negative 3. This is the remainder, and this is the quotient. Therefore, q of x is x squared minus 1, oops, here. X squared minus 1, and the remainder, negative 3. Oops, r of x. I don't know why I wrote that. It's negative 3. Okay. So depending on how you want to write your answer, right, p of x is the numerator, d of x is the denominator, and then you know q of x and r of x. So now you can arrange those pieces however you want to represent your answer, right? Whether it's like this or like this, doesn't matter. I would specify if I wanted it in a special way. So just keep that in mind, but you should be able to arrange your answer in either way. So let's do 14. give it a new page. Okay. So first thing we notice is, I'm even going to make this bigger so we can highlight it. Here, oops. We need to write p of x. So we need to start at x to the power of 5, and then we need to have x to the power of 4. We also need x to the power of 3, which we'll insert here. X to the power of 2, and then an x to the power of 1, which we'll also have to insert. So what we do is we just use coefficients of 0 to kind of bump this thing out. And you'll see when we're doing our division why we have to do that. Okay. So I'm going to move this over here. 27x to the 5 minus 9x to the 4 plus 0x to the 3 plus 3x squared plus 0x minus 3. Right here, we have to add those in, but we're adding 0, so that's allowed, right? 0 times x to the 3 is just 0. It's just a placeholder for the x to the 3. So now our divisor is a power of 2, right? Which, I don't know, we haven't seen before. Couldn't remember if the other one was, but so we have a power of 2 here, which means our remainder is going to be a power of x, right? Because I can only pull out a largest as an x to the 2. So what this is going to look like, but it still works, right, is we have 3x squared minus 3x plus 1 going into, and I'm a little bit worried because I'm not going to have that much space on the side here. So I'm going to write this out and then move it over as much as I can on my screen just so I can have room to do my scrap work on the side. 27x to the 5 minus 9x to the 4 plus 0x to the 3 plus 3x squared plus 0x minus 3. Did not leave a lot of room here. That's okay. I'll keep my scrap work here. Okay. In fact, I'm going to make a little bit more room up above here. I only need room for my quotient, but it just seems really crowded. So I'm going to bump everything down 1. There. That'll look a little bit nicer. Okie dokie. We need to work our way through each of these, right? So we're expecting it to be quite a lot of work. What's nice is that we're dividing by x to the power of 2, so it should go a little bit faster. But we still need to make our way through all these. So we start here, 27x to the 5 divided by 3x squared. So same procedure as before, right? 27x to the 5 divided by 3x squared. 27 divided by 3, I know you guys are better at math than me, but it's 9, right? So don't be afraid to use your calculator. I encourage you to use your calculator. There's no shame in using your calculator. In fact, there's more shame in doing this kind of math wrong. So, so just make sure you have the right number. So 9, and then x to the 5 divided by x to the 2. Remember power rules, right? So x to the 5 minus 2, right, because it's in the denominator. So it's x to the 3. So you get 9x to the 3. So up above this term here, I'm going to write 9x to the 3. 9x to the 3 times this whole divisor, 3x squared minus 3x plus 1. This is where I need more room. 9x to the 3 times 3x squared minus 3x plus 1 is going to be, all right, 27x to the 5th. 9x to the 3 times negative 3x is negative 27x to the 4th. 9x to the 3 times 1 is plus 9x to the 3. This whole thing gets subtracted down here. So we have 27x to the 5. It needs to be the same as here, right? It needs to go to 0. So just keep that in mind. Minus 27x to the 4 plus 9x to the 3. This is why we needed to have that x to the 3. Because if you don't bump it out and have an x to the 3, you might accidentally try to do 3x squared minus 9x to the 3, which you can't do, right? And so that's why we need to have this, this kind of spacing here so that we can do our subtractions properly. So this is being subtracted. So 27 minus 27 is 0. Negative 9 plus 27. Negative 9 plus 27 is 18. So plus 18x to the 4. 0 minus 9, negative 9x to the 3. And then what we do is we just bring down the rest of the terms here so we can start fresh. So plus 3x squared plus 0x minus 3. Okay, now we start all over again, right? We take 18x to the 4 divided by 3x squared. 18x to the 4 divided by 3x squared is 18 divided by 3 is 6. X to the 4 divided by x squared is x squared. Makes sense because our next number should be 1 degree less than the previous one, right? So if you're checking your work, that's one way to do it. So plus 6x squared. 6x squared times 3x squared minus 3x plus 1. Here we go. 6x squared times 3x squared minus 3x plus 1 is going to be, okay, 18x to the 4 minus 18x to the 3 plus 6x squared. All right. Subtract it. 18x to the 4 minus 18x to the 3 plus 6x squared, all being subtracted here. 0, negative 9 plus 18 makes positive 9x to the 3. 3 minus 6, negative 3x squared. And then, of course, bring down your 0x minus 3. Plus 0x minus 3. Okay. Next thing I need to do, 9x to the 3 divided by 3x squared. All right. Slowly, we're probably getting the hang of this. Right? If not, you just keep doing more of them until it makes sense. So 9x squared, or 9x to the 3 divided by 3x squared makes 3x. Again, 1 degree less than this previous one, so it checks out, plus 3x. Now 3x times the divisor, 3x times 3x squared minus 3x plus 1, so many 3's, 9x to the 3 minus 9x squared plus 3x. So that's what I'm going to subtract. 9x to the 3 minus 9x squared plus 3x. Subtract that. 9 minus 9, oops, is 0. Negative 3 plus 9 makes positive 6, so plus 6x squared. And then 0x minus 3x is minus 3x. And then bring down that minus 3. Okay. This is my last division, right? Because once I've divided out x squared, this is the highest term here. right? And so I won't be able to pull out any more multiples of x squared. So that's how I know that this is my last step. Okay, so 6x squared divided by 3x squared is going to be 2. So here, and notice, right, x was my last number, and so I'm expecting just a constant here, and that's what I'm getting, so plus 2. I think it was positive, yeah. So now 2 times the divisor, oops, 2 times 3x squared minus 3x plus 1 is going to be 6x squared minus 6x plus 2, which is what I'm going to put in here, 6x squared minus 6x plus 2. Subtract all that. So now I'm here, it's hard when I'm all the way over, but 6x squared minus 6x squared is 0. Negative 3 plus 6 plus 3x, negative 3 minus 2 minus 5. Okay. So notice our quotient or our remainder is a polynomial, right? And that's okay. So our q of x is 9x to the 3, and I should bump this down a line. 9x to the 3 plus 6x squared plus 3x plus 2. And r of x is 3x minus 5. Okay. Which you can arrange however you'd like. All right. Write as p of x over d of x is equal to q of x plus r of x over d of x. And p of x is q of x, d of x plus r of x. Okay, so p of x is this whole thing. You can actually drop the zeros. It's this one, and d of x is this one. Maybe I'll copy this one so I can bring it down here and just have for reference. Whee. So I'll say or this. So p of x, I'm going to do this one because it's a little bit easier to write. Or you know what? Let's do this one. So we have p of x is 27x to the 5th minus 9x to the 4 plus 3x squared minus 3, just copying it out, divided by d of x, which is 3x squared minus 3x plus 1, is q of x, which we found was 9x to the 3 plus 6x squared plus 3x plus 2, plus r of x, which is 3x minus 5, divided by d of x, which is 3x squared minus 3x plus 1. There, done. Okay, so quite lengthy, but notice we're just doing the same thing over and over and over and over again, right, until we get to the very end. And then we have our quotient and our remainder. So after that, after you kind of get into the groove of it, as long as you remember to bump out any missing x's, then it should be okay, right? And it's actually kind of fun once you get the groove of it. Okay. Any questions about that before we keep going to the last section in chapter 3, 3.6? Okay. So then let's go to 3.6. 3.6, if, oh, that's not the right one, here, is the last page of that handout or the notes that I posted. Notice that it's just one page long, and I say just kind of carefully, because we're going to be graphing rational functions. Rational functions, remember, are a polynomial divided by a polynomial. So we were just doing polynomial long division, so we know how to divide these things, but that's not quite what we're doing here. We're going to be graphing these things. So what happens is we're going to end up with potentially vertical asymptotes, horizontal asymptotes. You might remember asymptotes from a previous math course, right? It's where a graph is approaching, but it never actually gets to that point. That's an asymptote. So that's what we're going to be talking about. So 3.6 is on rational functions and their graphs. We've already talked about rational functions. A rational function is a polynomial over a polynomial. So a rational function is a polynomial divided by a polynomial. Okay. Some assumptions that we're making, at least to begin with, is that this polynomial and this polynomial have been simplified so that they don't have any common factors, right? So here, what we usually call these is P of X over Q of X. I think it's Q of X. Yeah. And we assume for now that P of X and Q of X have no factor in common. We assume P of X and Q of X have no factor in common. But if you scroll down or kind of have a glimpse down at the bottom of the page, let's see what it says. Because I want to remember, is what we do with the common factors. So it is called common factors in the numerator and the denominator, and what we do there. It just makes a little hole, and then, but we'll probably get there today, hopefully, or next day. So we assume that the numerator and the denominator have no factor in common, or factors, I should say, in common. This is assuming or saying they have been simplified. Or maybe I'll just leave that. Okay, so we assume that they have no factor in common for now. Okay, so there's a lot of stuff going on here, and I just want to walk us through these notes before we even look at any questions, or any problems, I should say. So there's quite a bit of information in here. Eventually, right, if you have a glance at the type of question that I expect you to be able to do, they're all the same type, right? And so here we're just graphing rational functions. You'll see it's a lot of work, right? But we're going to find the intercepts. We already know intercepts from from lines and from quadratics. So we were graphing quadratics, and that's probably the most similar to what we're about to do. But the intercepts we find the same way. The x-intercepts are where y equals 0, and the y-intercepts are where x equals 0. So we find the intercepts and the asymptotes. That's the new part for this. And then we sketch a graph of the rational function and state the domain of range from the graph. And then here's a key part, right? It even says, use a graphing device to confirm your answer. So I want you to use Desmos to confirm your answer. because really all we can be expected to do here, this kind of modern day that we're living in, I'm just expecting to see a sketch of the graph. Do you understand the general behavior of this thing, right? How does it behave around the asymptotes? Where does it cross the x-axis? And then, of course, we leave the actual graphing to Desmos or something else, right? Some other graphing tool. Okay, so let's see here. I'm going to bring this in here. Okay. Let's first talk about what the vertical and horizontal asymptotes are. And then we can talk about how do we find them, how do we figure out what the behavior is, right? But so what we have is, let's say we have a horizontal asymptote at x equals a, so just some random point x equals a. Then how this function behaves is going to depend on if it's coming in from the left or from the right. So if it's approaching a from the left or from the right. So what we do is we use notation here. As x approaches a from the right, so from the positive side, we say a to the power of plus, which is hard to see here. So that's why I'm going to write it out. But if we're approaching a from the left, we do a to the power of the negative. And depending on if y, so if the function is going up, 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 or if it's going down, 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 right, we use y is approaching infinity as x is approaching a from the right, that type of notation. So we use x is approaching a plus, right, to say as x approaches a from the right, and x approaches a from the left, right, to say as x approaches a from the left. We describe the behavior of the function by either y is going to negative infinity or y is going to positive infinity. Those are our two options. We describe the behavior of the function by either y is going to negative infinity or y is approaching positive infinity, right? So here, if it's going kind of down, down, down as you approach an asymptote, or if it's going up, 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 right, then y is going to positive infinity. Okay, so those are our vertical asymptotes, right? And we will talk about how we find those, but for now, right, we just need to be comfortable with this notation. So we're approaching a from the left, a from the right, and then same thing with the horizontal asymptotes, except now they're horizontal instead of vertical. So now we've got this asymptote where this function is going to get close to, but never actually get there, right? And so here, y is going to be, right, it flattens out at b-ish, close to b, or approaches b as x is going to positive infinity. And here, as x is going to negative infinity, y approaches b. So this is another way that you could approach this, this horizontal asymptote. Same type of notation though, except we're talking about y approaching some constant instead of x approaching some constant. And then x is going to positive or negative infinity. Yeah. Okay. So let's see here. How do we find these asymptotes? Let's put that in here. Okay. Finding asymptotes of rational functions. This one is going to be used a lot, so I am going to highlight it here so I can find it easily. I suggest you do the same in your notes. Just make sure that you have access to this one, because sometimes the asymptotes can be kind of tricky to find if you don't have this. If you do have this, it's easy, right? So if we have this rational function, notice that we just have a general polynomial over a general polynomial. So we're allowing these polynomials to be whatever we want. This is a polynomial degree n, and this is a polynomial degree m, right? And so notice down here, we're going to be comparing the degree of the numerator and the degree of the denominator, and that's going to determine our horizontal asymptote, right? So these are just things that we need to kind of pay attention to. But the first thing we want to talk about is the vertical asymptotes. So the vertical asymptotes are where the denominator of this thing is equal to 0, right? So let's say here, the vertical asymptotes, I'll say of P of X over Q of X are at values of X that make Q of X equal to 0. I'd say the easiest way to, depending on what Q of X looks like, we're not going to deal with huge Q of X. So let's just look at the examples or those questions that I expect you to be able to handle. And so if we go back here, if we glance at Q of X, well, these ones are nice and simple. This is a quadratic. We know how to factor quadratics. Quadratic, 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 already factored. Hey, that's nice. Quadratic, 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 quad, 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 quad. Good. Cubic. X to the 3, but it looks like I can pull out a common x squared to get x squared times x minus 3, so pretty easy to factor. Quadratic, 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 quadratic. We can factor quadratics, okay, using the quadratic formula. And we'll go through and we'll do one together. Or we'll do more than one. But just as a heads up, right, I'm not expecting you to be able to do these huge, huge functions, but we need to be able to factor quadratics at least. So, like I said, the easiest way to do that is to factor Q of X. Okay. The easiest way to do that, to find the zeros of Q of X, to find the zeros, oops, 0 is, of Q of X is to factor it. Okay. So let's just put that on the back burner. Okay, so what we would do is we would factor this thing, figure out where Q of X is equal to 0. Those are where the vertical asymptotes are going to happen. Okay, we're not going to deal anymore with it, because if we have a glance at the notes, it's actually all laid out for us in here. right? We've got a step-by-step formula or procedure for doing all these things. So I'm just laying out the groundwork, and then we're gonna go back and we're gonna fill in the gaps. So vertical asymptotes, right? Vertical asymptotes are the lines at x equals a, where a is the 0 of the denominator. So that's what we're dealing with here. Horizontal asymptotes, so the second one, horizontal asymptotes depend on the degree of the numerator and we call that n. The numerator, right, is p of x. And the degree of the denominator which we'll call m. The denominator is, of course, q of x, as long as we've written it like this, p of x over q of x. So n and m, right, help us figure out how these things, so if n is less than m, then this whole thing has a horizontal asymptote at y equals 0. That's just true. If n is equal to m, then we have a horizontal asymptote at an over bm. Notice an over bm is just the two leading coefficients divided by each other, right? And so if they're equal, so if you find x squared, for example, which we had for a lot of those problems that we just went through and looked at, then the leading coefficients divided by each other is the horizontal asymptote. If n is larger than m, then there are no horizontal asymptotes. So that can happen. That's actually pretty common. But these are our options, okay? So here, if n is less than m, then the horizontal asymptote, I'll shorten it here, horizontal asymptote, we often write HA, and of course vertical asymptote is BA. So if n is less than m, then we said there's a horizontal asymptote at y equals 0. If n is equal to m, then it's going to be a horizontal asymptote at an over bm, right, which is leading coefficient of p of x. I'll scoot this over so I can kind of divided by the leading coefficient of q of x. Right. Kind of the most fun one, but the most to remember too. And if n is larger than m, then there's no horizontal asymptote. Okay. So these are our options. I'll scoot this over. For the horizontal and vertical asymptotes. So that's how we find them. Of course, we're gearing up to do a huge example here, but that's what we're about to be doing, right? We also need to figure out the behavior around these asymptotes, and that's what we're kind of getting to. Okay, so now that we've talked about, okay, well, how do we figure out where these asymptotes are? Now we can work up towards sketching rational functions. And like I said, these aren't going to be perfect because we're not graphing calculators. But you should have a pretty good idea of what this thing is going to look like. So okay, make this nice and big. Did we talk about the intercepts yet? No. Okay, so before I do that, okay, I'm not going to put this in quite yet. We've already talked about the X and Y intercepts, but I want to outline what they are again up here so that we have all the information that we need. So recall the X-intercepts are where y, which is also f of x, is equal to 0. So where this whole function is equal to 0. So in r of x is equal to p of x over q of x, right? So in this rational function where we have p of x over q of x, this can only equal 0 if p of x is equal to 0, right? Sorry, not just this. This can only be 0 if p of x is equal to 0, right? Because we can't divide by 0, and so, because that's illegal math. So the only way that we could make this whole thing be equal to 0 is 0 divided by something. 0 divided by 2 is 0. Right, so the only way that we can force this to be 0 is if p of x is equal to 0. Just like with the vertical asymptotes, the easiest way to figure out where this thing is 0, find the zeros of p of x, is to factor it, right? And so if you have a glance at those questions at the bottom of the page, what I'm expecting you to do is are pretty simple, kind of quadratic. So we should be able to factor those pretty easily by now. But right, if not, you've got lots of good practice here, so you will be really good at it. Right, so here, the easiest way to figure out where this thing is 0 is if we factor it. Okay, so the easiest way to find where p of x is equal to 0 is to factor p of x. Okay. So, and then the results are going to be our x-intercepts. The zeros of p of x are the x-intercepts. Okay, we're just leaving room for more than one x-intercept, right? Quadratics, even quadratics, we have 2 x-intercepts. But we also said there are some instances where we can have no x-intercepts. That can happen. So just if you're factoring a quadratic, for example, then what you might find is that you take the square root of a negative number, which can't happen. So then there are no x-intercepts because there are no zeros. So x-intercepts, and I'm going to underline this here, are where the function is equal to 0, right? And so if we talk about the y-intercepts are the easiest ones. The y-intercept is where x is 0, right? And so the y-intercept, usually there's only one, are where x is equal to 0, right? the easiest way to do this is just to plug in x is 0 into the original equation. Especially if you've spent some time factoring, and maybe you're lazy and you don't want to figure out if your factoring is correct, then you might be plugging into the wrong equation, which you don't want to do. But if you're factoring, you should be double checking to make sure you get back to the original equation. Right? Sometimes we're in a hurry and we don't want to do that though. But the y-intercept is where x equals 0, right? The easiest way to find this the y-intercept is to plug in x equals 0 into p of x over q of x. Which is actually equal to y, right? Y is p of x over q of x. Okay. It is possible to not have a y-intercept. Okay, so that can happen, especially if you plug in, and we'll see an example, hopefully we have time, but if we plug in x equals 0 into q of x and q of x becomes 0, then we're dividing by 0, which can't happen, right? And so then we wouldn't have a y-intercept. So I would recommend putting it into the original equation. If you're feeling confident with your factoring, you can put it into the factored equation, right? So I say factored equation because, well, here the easiest way to do it is to factor p of x. The easiest way to find vertical asymptotes later is to factor q of x. So now we're ready for that step-by-step procedure, which actually starts with let's just factor these things, right? Let's just put in the work, factor p of x and q of x, and then plug them in. So now we're ready for this procedure. So to sketch a graph of rational functions, like I said, the first thing you're going to do, and I want you to walk through each of these steps for each of those problems that I have on that page. So factor the numerator and the denominator. Right? This is going to help us find the x-intercepts as well as the vertical asymptotes. Then you can deal with your intercepts. So find the x-intercepts by determining the zeros of the numerator, right? So that's why we factored the numerator initially, and the y-intercept from the value of the function at x equals 0. So that's what we just said, right? It's just a little bit cleaner the way they said it, right? But I wanted to explain it. But it's all here, okay? The vertical asymptotes, that's the next thing we deal with. So once we have our intercepts, right, we can plot those if we want, if we're trying to build our sketch as we go. The vertical asymptotes, you're gonna find the vertical asymptotes by determining the zeros of the denominator, right? And then you're gonna see which direction y goes in on each side of the vertical asymptote by using test values. So what we do is we take test values, just like we were using test values for inequalities to figure out if it was pointing up or pointing down, right? So we do the same thing, but we take test values getting closer and closer to that asymptote, or maybe it's like this, right? We'll see an example and it'll make more sense. Okay, but we've used test values before, and so that's the same idea that we're using here. And we just need to know, is it going to positive infinity or negative infinity? So we're actually only going to deal with the sign of this thing again, right? We know it's going to go to infinity, but which direction? Then we can look at the horizontal asymptote. So find the horizontal asymptote, if there are any, using the procedure described in the box, in the highlighted box that we put on the page. So here in the box highlighted above, right? We look at the degree of the numerator and the degree of the denominator and how they compare, right? If the degree of the numerator is less than the denominator, then the horizontal asymptote is at y equals 0. If they're equal, then it's the two leading coefficients as a fraction is your horizontal asymptote. And if if the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. Great. Then we have enough information to start sketching the graph for real. So what you can do is you can kind of start sketching things out as you go here, but then here we're going to put it together. There will be times where you might have to find additional points, okay? And it's hard to know when you need to find additional points. But what you're going to do is, so as needed is kind of hard when you're first beginning, but there will be portions where you're like, hey, what does it look like in this section, right? And so then you might look at little values of x and evaluate the function, the original function, at those points, and then you can plot points and connect the dots, okay? The key thing here is we're trying to sketch the graph of that function that you're given, right? And if you think about a graphing calculator, Desmos, for example, all they're doing, they're not drawing a line. All they're doing is just evaluating the function at many points of x, right? And then it's just putting all those points next to each other, and that's what they're doing. So you can do that too. It's going to take a long time. But if you really want to sketch a graph of a function, that's what you can do, and you can use these as guidelines. That's not something that I want you to really dive into, but it is what you're doing, right? You're trying to sketch this thing. I'd say once you've kind of got these first four things done and you've made a quick sketch of this graph, then go to Desmos and just kind of make sure that you're on the right track. And ultimately, we're going to use Desmos to graph things when it really matters, right? And so, but knowing all these behaviors will serve you really well, especially in calculus, right? And so, and this is pre-calculus, so that's why we're here, right? And so, knowing all these things. And being comfortable with finding them, that's the key part. The actual sketch, I don't really care about, because you can use Desmos. All right. Let's see, are we ready for an example? Let me see if I can, I'll just check my notes here quickly. Okay. Good. So these problems are going to be really large, right? There's a lot of things, or there are a lot of things that we need to do. Okay, but let's go through, and just as an example, okay, if I ask you to graph r of x is 2x squared plus 7x minus 4 divided by x squared plus x minus 2. Okay, so we're going to go through all these 5 steps, right? And then, of course, we're going to make sure we have the right graph with Desmos. And then we'll use the graph to find the domain and range, and state the domain and range. So here we have a polynomial, degree 2, with a leading coefficient of 2, right? All things that are going to come up potentially later. Down here in the denominator, we've got a polynomial, quadratic, right? Both of these are quadratics. A polynomial degree 2 with a leading coefficient of 1. Okay. Already, we know what the horizontal asymptote is, right? These degrees are the same, So we know it's going to be 2 over 1. There's a horizontal asymptote at 2. Right? So we already know a lot about this without even starting. Okay, so the first step, right, is to factor this thing. Okay. I can't remember if we've factored things like this or if I forgot to have an example of it. So I want to factor something like this. I always use the quadratic formula, right, to figure out, the quadratic formula tells me where the zeros are, right? But then if I have to factor it, I have to do a little bit of work if there's a fraction involved. So 2x squared plus 7x minus 4, okay, as a quadratic is a equals 2, b equals 7, and c equals -4. So x is negative b plus minus the square root of b squared minus 4ac over 2a. So I find -7 plus minus the square root of 7 squared minus 4 times 2 times -4 divided by 2 times 2. So I get -7, and of course we should be pretty comfortable using the quadratic equation right now. So 7 squared minus 4 times 2 times -4 puts me at 81. The square root of 81 is 9. So I get plus minus 9 divided by 4. So what this says is that x is -7, and I want you to use your calculator for this, right? Plus 9 is 2 divided by 4, so 1/2. And x is -7, whoopsies, -7 minus 9 divided by 2, or divided by 4 rather, is -4. These are the zeros of the numerator. Remember the zeros of the numerator, okay? The zeros of the numerator are the x-intercepts, okay? These are the zeros of the numerator, which are the x-intercepts. Okay, but what I'm working on is I'm trying to write this out as a factor. Okay, use these to factor the original 2x squared plus 7x minus 4. 2x squared plus 7x minus 4 is going to be, well, it's going to be equal to 0, right? That's where I'm finding these zeros. It's equal to 0. Okay. What I'm doing is I'm forcing a 0 here because I found the values where this thing is equal to 0. So I'm allowed to do that, and you'll see why I'm doing it in just a little bit here. So times x minus 1/2 times x plus 4, right? That's the same method that we used before when we were factoring with whole numbers, right? But now we've just got a fraction here. And so what I need to do is I don't want to have a fraction here. What I'm going to do is I'm going to multiply by 2, right? 2 over 2, each term in this one here. So it becomes 2x over 2 minus 1 over 2 times x plus 4. All that, we're forcing it to be equal to 0. Okay. What happens here is I can pull out a common 1/2. So now I get 0 is 1/2 times 2x minus 1 times x plus 4. This 1/2, I can multiply 0 by 2 and it just kind of gets absorbed, right? And so that's what I'm doing in order to get rid of this fraction. So I get 0 times, oops, I'm following this 2 around here, is 2x minus 1 times x plus 4. So this thing is equal to 0. 0 times 2 is 0. And now what I want you to do is I just want you to check it to make sure you end up back here. So let's just check. 2x minus 1 times x plus 4 is 2x squared. 2x squared plus 8x minus x minus 4 plus 8x minus x minus 4, which is 2x squared plus 7x minus 4. Whee! Okay. So that's how we're going to do it, right? If you get a 0 as a fraction, right, the fraction is still the 0, right? Especially if you look at here, if you make this be 0, 2x minus 1 is 0, well then you'd have 1 over 2 as your x, right? So you could solve this, set this equal to 0 and solve for x again. Okay. All right, great. So now we've got the numerator factored, right? And in doing so, we also found the X-intercepts. We're gonna parking lot those for a little bit, because up here, right, we're doing a lot of work in step 1 where we're factoring. Now I need to factor x squared plus x minus 2. Now factor the denominator. X squared, I have it here, x squared plus x minus 2. Again, I've got this, I've got a quadratic. You can probably see what the factors are, but if you can't, I always had a hard time seeing what the factors are, so I always just use the quadratic equation, right? So we can do that again, and you'll get really good at using the quadratic formula. So A is 1, B is 1, and C is -2. So X is negative b plus minus b squared minus 4ac over 2a, oops, there. -1 plus minus 1 squared minus 4 times 1 times -2. 1 plus 8 is 9. And 2 times 1 is 2. So we get -1 plus minus the square root of 9 is 3 divided by 2. So x is equal to -1 plus 3 puts me at +2 over 2, 1. And x is -1 minus 3, that's -4 divided by 2, which is -2. Okay. These are the zeros of the denominator, which are also, later on, we'll find that they are the vertical asymptotes. These are the zeros of the denominator, which are the vertical asymptotes. Okay. Because we've got whole numbers, we can just use them to develop our factors. And so factoring, oops. we were doing x squared plus x minus 2 is going to be x minus 1, right? If x is positive 1, it has to be 0 times x plus 2. Okay. You can check, just double check that you actually expand to the right thing. It's worth it. You're going to be using these factored things a lot. So here we're going to check x minus 1 times x plus 2 is equal to x squared plus 2x minus 2, which is x squared plus x minus 2. Whee! Okay. So now we've factored both the numerator and the denominator. Okay. So we can write r of x is 2x squared plus 7x minus 4 divided by, now just writing out the equation again, x squared plus x minus 2 is going to be the same as, and we found 2x minus 1 times x plus 4. 2x minus 1 times x plus 4 divided by the factors we just found, x minus 1 times x plus 2. Okay. All right, step 1, factoring, done. I think it might have spanned 3 pages. 1, 2 pages, not bad. And these are small pages in here. So not bad. The second thing we're gonna do, right, is we're gonna find the intercepts. We've already done a lot of that work, right? The x-intercepts we said are at x equals negative, x equals 1/2 and x equals -4. So highlighting that these are the x-intercepts up here, right, saves us some work down later. And so here, x equals 1/2 and x equals -4 from above. Right, we already did that work, so I'm not going to redo it. There's no point. But I do need to say where I'm getting this from, right? When I'm getting you to show your work, right, you can't just tell me that these are the x-intercepts and you haven't shown me any work. That doesn't work. Work. The y-intercept, oops, singular, typically, is where x equals 0. So what I'm going to do is you can use the original equation, this one, or this one. I think it might be easiest to just use, or the safest way to do it is just to use the original equation, right? And so I'm going to steal this here. Copy. Paste. So r of 0 is 2 times 0 squared plus 7 times 0 minus 4 divided by 0 squared plus 0 minus 2. Evaluating this is pretty easy, right? We get -4 over -2. And so this becomes -4 divided by -2. So y equals 2 when x equals 0. Y equals 2 when x equals 0. So the y-intercept is at 0, 2, right? And I guess I should probably write these as intercepts as well, right? The x-intercept is when y is 0, and so it's at I guess I should use 1/2, 0, and -4, 0. Those are the points, right, that we're plotting. Okay, we're doing good. So if we work through, where's our list of things to do? It's way, way, way back here. Okay, so we found our intercepts. We have our X and our Y intercepts. If you want to, if you're curious, you can plot those to kind of get an idea of what's going on. Otherwise, the next thing we're going to do is to find the vertical asymptotes. I would argue this is the hardest step of all this, right? And so we need to figure out how to use these test values properly. So the vertical asymptotes, we already know where they happen, right? From factoring the denominator, x equals 1 and x equals -2 are the vertical asymptotes. So we know where they happen, we just need to know what happens around there. So the vertical asymptotes we know from above we have vertical asymptotes. Where did we say? X equals 1 and x equals -2. Just so I don't confuse myself, I'm going to write x equals -2 and then x equals 1 as they would appear on a number line. That's just because I know I get confused about that kind of stuff. So at x equals -2 and x equals 1. Okay, so we know at these points we have some sort of whoosh whoosh action, right, where the function will never be anything at x equals -2 or x equals 1, okay? But we need to figure out how it behaves. So what I do, and what I encourage you to do, is to make another number line. So just like we did before with the inequalities, where is it positive, where is it negative, that's all we need to know. We know this function is gonna go to infinity. It's just a matter of if it's positive or negative. And so we just need to figure out the sign of this thing, just like we did before with inequalities. So just like that. And maybe I'll give myself a little bit more room. The reason is I need to figure out what happens as I approach -2 from the left, as I approach -2 from the right, as I approach 1 from the left, and 1 from the right. So there's going to be 4 calculations, right? Kind of one on either side of the vertical asymptotes. And just to kind of split up my work here, and here, I'm going to remove this one later. But like I said, I need to figure out how this thing behaves approaching -2 from the right and also 1 from the left. So I need to split my work up here. So that's why I'm doing these ones. And then I'll delete these because they're not asymptotes. The asymptotes are here and here. Okay. So up here, right, what you can do is just pick test points close to the asymptote, okay, on either side. Pick test values close to the vertical asymptotes on either side. Okay. For example, on the number line, remember, this might be -2.1. It's increasing on the negative side. This might be -1.9, right? So just, you can pick any values, but -1.9, right? Just make sure that you're coming in from the right direction and coming up on -2. Same thing with the 1. So maybe this is 0.9 and this is 1.1, right? I always just like to move us a smidge off of the vertical asymptotes. Okay, how do we figure out what the sign is here? So what we're doing in each of these little sections here is we're looking at as x approaches -2 from the left, as x approaches -2 from the right, as x approaches 1 from the left, as x approaches 1 from the right, right? Using that notation that we established. And then our goal is to figure out how y behaves. Does it go to positive infinity or negative infinity? Now the key is to use the factored function. So here we have the factored equation, right, or the factored rational function. So here I'm going to copy this and put it off to the side here. I'm going to shrink it up a little bit. This is where I'm going to be plugging in my test values to see if I get a positive or negative result here. And so let's see. If I'm just using -2.1 times 2 minus 1, I get a -4 something minus 1. Well, that's going to be a negative number. So all I need to do is I need to denote that with a negative number, right? So then, what else do I need to do here? Next one, -2-ish plus 4, right, puts me at a positive number. Same thing, -2.1 minus 1 puts me at a negative number. And then -2.1 plus 2, well, it's on this side of 2, or -2, so it's going to be negative as well. So we get a negative times a negative, whoops. So you have a, same idea as before, right? Negative times a positive is a negative, divided by a negative times a negative, which is a positive, so overall you have a negative result. So what does that tell you? It tells you that y is going to negative infinity. Right? It's going to be infinity, it's just whether it's positive or negative. What does this thing look like? Well, it must look like wee, right? So here, right, this might look like woo, like this. Okay. Moving on to the other side, right? So now I'm approaching -2 from the right. So now I'm going to use something that's slightly to the right of -2 as my test point, but I do the same thing, right? And so -1.9 times 2, so -2 times 2 is -4-ish, minus 1 is still negative. -2-ish plus 4 is positive. -2-ish minus 1. It only matters over here, right, where you're close to 2. -1.9 minus 1 is negative. And -1.9 plus 2 is positive. So overall here, I've got a negative over a negative, which overall is a positive number. So what that looks like, right, is that y is going to positive infinity. So that means, oops, not that one. That means here, it's going up like that. Okay. Remember, this is just a divisor. I was using it as a vertical asymptote. It's not. But now we do the same thing with 1. So like I said, the vertical asymptotes are the most work, I think, because you have to figure out how this thing behaves at all the vertical asymptotes. But once you get in the groove, it's not that bad. So using 0.9, 2 times 0.9 is 2-ish minus 1, so that's going to be positive. 0.9 plus 4 is positive. Divided by 0.9 minus 1, that's negative. And 0.9 plus 2 is positive. So overall, I get a negative number, right? A positive over a negative is a negative, which tells me that y is going to negative infinity. Looking like that. Same idea, 1.1. I always like to deal with positive numbers. I don't know. It's just easier. 2 times 1.1 is 2.2 minus 1, which is positive. 1.1 plus 4 is positive. 1.1 minus 1 is also positive. And 1.1 plus 2 is positive. So overall, I have a positive result, putting me here, something like that. Oops, I forgot to write y. Y is going to positive infinity, which might look like this. Okay. A lot of work here, a lot of work, but that's what you need to do for your vertical asymptotes. All right. Step 4. Almost there. Going back to our list here. Figure out our horizontal asymptotes. So find the horizontal asymptotes if there are any. There are cases where there are none, right? When is that? When the degree of the numerator is larger than the degree of the denominator, right? And so I'm actually going to steal, because it's been a while. I'll steal this and bring it down. Ooh. Could write a summary, I guess, too. Step 4, horizontal asymptotes. Oops. We'll just have one. So here we have to remember, oops, this image. In our case, right, let's go back and look at our original equation here. R of x is this one. Okay. So from here, right, I know my n is 2, my m is 2, a subscript n is 2, and b subscript m is 1. Okay, so I have all that information here. The reason I needed an and bm is because n is equal to m, right? So what I'm going to say is that since n equals 2, which is also equal to m, there is a horizontal asymptote. I'll say HA. I hope I defined it. I'll define it here. If I haven't, I think I did though. Vertical asymptote, horizontal asymptote might make it a little bit easier. There is a horizontal asymptote. I'll put that up here. At y equals an over bm, which in our case is y is 2 over 1, so y equals 2. Okay. So, like I said, I don't really expect you to do a flawless graph of this thing, but knowing all these things, we should be able to do a pretty reasonable graph. So sketch the graph. Okay, we compile all this information into one graph, and we'll see how I do here. something like this. Don't really know if this is going to work or not, but here we go. Going back to our first step, what did we find in our first step? Well, that was our factoring. We also found that's where our vertical asymptotes are and our x-intercepts, but they come up later. So my x-intercepts are at negative or 1/2 and 0 and -4 and 0. So I'm going to put those on, as well as y equals 2 is my x-intercept. So I'll start with my intercepts. 1/2. Let's say this is at 1/2. And let's say this is at -4-ish. I'm just drawing a sketch, so you might be able to spend more time on it, but let's say this is at 2. Okay. 0, 2, and 1/2, 0, -4, 0. Let's do it properly. Right, our 2 x-intercepts, our y-intercept. All right. Then after our intercepts, we dealt with the vertical asymptotes. We have a vertical asymptote at -2 and 1. So I'm gonna just kind of dot my lines there. -2 would be somewhere around here. And 1, right? Okay. They're my vertical asymptotes. I also figured out the behavior of these things as I go and approach the vertical asymptote. So it looks like it's going to look like kind of like wee, wee. Okay. So before I draw these lines, I need to take into account my horizontal asymptote. So I'm also going to dot lines at my horizontal asymptotes. So my horizontal asymptote is at y equals 2, which also happens to be my my y-intercept. So, oops. So here's my horizontal asymptote. This is my vertical asymptote, vertical asymptote. Okie dokie. So what does this thing look like? There are a couple of options, right? But what I know is that the horizontal asymptotes, they tell me the behavior as x is going to -infinity and +infinity. Now, I need to look at how the thing or the function behaves approaching -2 from the left and approaching 1 from the right. So coming in from -2 from the left, I know it's going down, right? And so so what we can do is we can use that to figure out the behavior around the horizontal asymptote. So we know from before, right, that this thing is going to be going down, 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 down. If it's going down and this is the horizontal asymptote, well, then it's going to be approaching that horizontal asymptote, but never get there. So here, I'll just indicate that by kind of pushing it up against that horizontal asymptote. Okay. And the reason it's pushed up from the bottom, right, it could be pushed up from the top, but from the bottom is because we already determined that it has to go down here. Okay. So I'm going to use the same idea on this side. I think it was going down. If it was going up, right, then it would have to rest on the horizontal asymptote from the top, right? So let's see here. Coming in from the right, it is going up. So that's what we're going to draw. So coming in here, it comes from the top. And because we've got this horizontal asymptote, oops. It's going to kind of Well, that wasn't a very good one, was it? It approaches the horizontal asymptote, but it never gets there. Okay. So for the horizontal asymptote, it just depends on the behavior as you go to x equals negative infinity and positive infinity. And so, so you use that along with your vertical asymptotes to figure out where this thing is. Okay. I guess I did a poor job because it was supposed to go through here, but I can make that happen. Totally forgot about my X-intercept. There, that's better. Okay, next thing I know is I know the behavior of this thing, right? As I approach -2 from the right, it's going up and then going down on the other side. I also know that I have to go through here and I have to go through here. So it looks like I might be able to go something like this and maybe like this. Remember, we're just sketching. Oh, I'm going to put that closer to the vertical asymptote, right? Remember, it's just a sketch and I'm out of time. But we can check in Desmos to make sure that this is right, but it's pretty close to what the actual graph would look like, right? And so the really complicated graph that we've sketched, but as long as you follow those steps, you're safe, okay? I know I'm out of time. We'll do another one next day. Are there any questions? But definitely work through some of those on that page to see if you've got the hang of it or not. Any questions? If there are none, have a great weekend, and I'll see you on Tuesday.
Thank you, you as well.
Thank you.
Thank you. Yeah, you too. Bye.
Bye, guys.